Okay, so today's lesson is probably the most important lesson of this unit, and it's optimization. Okay? We've talked before about optimization. We've talked about how important is optimization as a person, as a business, as everything, right? Even if in your real life situation, where if you are, for example, to build something, right? Or if you are to fence something, or if you are to create something, you want to always get the most out of it and spend the least, right? It's all of us, right? We want to have the biggest thing, but with the least amount of material to use, right? We talked about yesterday about how can I, like if I give you a certain perimeter, right? If I give you a certain length, and I want you to make a shape out of it, a square or a rectangular shape, what did you guys figure out with the area? What gave you the maximum area? What shape? Square. A square, right? And then we figured that the square is going to always give you the maximum area, given a perimeter, right? And square is your optimal shape. Square is your optimal shape for rectangular shapes, right? And we talked about if it becomes 3D, right? It becomes a cube, right? A cube would give you your optimal shape. So the purpose of optimization, again, is to reduce the amount of material we're going to use and to increase the area or the volume that we have. Yes? So the purpose of optimization is to, do we maximize or minimize surface area? Minimize, because surface area is the amount of material we're going to use. And maximize the volume. And in this case, we are talking about 3D shapes, right? So that's why we're using the surface area and the volume. When we're dealing with a rectangular prism, the optimal dimensions will always be that of a what shape? What rectangular prism shape gives you the optimal values? Square. 3D shape? Cube. Cube. Are you guys okay with this? All right. So when we're looking at a cube, eyes on the board for a second, please. So when I'm looking at a cube, I won't have length, width, and height anymore, right? Because the length and width and the height, they're all the same size, right? So do I need to use L, W, and H? No, because they're all the same, right? I can use the same letter for all three of them, right? So instead of using L, W, and H, I can use S, S, and S, or A, and A, or whatever. It's the same thing, right? Because my length, my width, and the height are exactly the same thing. So I can use S, S, S for all three dimensions. Do you guys understand that part? Okay? Now, if I'm looking at a cube, right here, I think that's a cube right here. That's your cube, right? You have the same side length for all shapes, right? For all the sides. Now, if you're looking for the surface area, what would it be?
Surface area?
Yeah.
All the sizes added.
All the area of all the sides added. How many equal sides do you have?
6.
6 equal faces, right? So you have 1, 2, 3, 4, 5, 6. What's the area of this one?
The same one as the other.
What's the area of this? Side times side is side squared, right? So it's side squared because length times width, but in this case it's side times side, right? So side squared. So I have 6 times the side squared, yes? Okay, so the area of this one, of this side, is side times side, which is side squared, right? I have 6 equal sides, so that means my area or my surface area is 6x squared. So instead of using the one for the rectangular prism, which is 2 times LW plus LH plus WH, then I'm going to use the surface area of a cube, which is 6x squared. By the way, this is not on your formula sheet, so you need to know this. Okay? The surface area of a cube is not on your formula sheet. Now, what's the regular volume of a rectangular prism? The volume of a rectangular prism is length times width times height, right? So length times width times, sorry. Can't even do this, sorry. So length times width times height, yes? Now in this case, the length is S, the width is S, and the height is S. So what does this become? S cubed. So the volume of a cube is S cubed. Are we okay with this? Are we okay with the formulas? All right. So here's a question. So the question will be, the volume of a box shoe or shoe box is 5,000 centimeter cube. Calculate the optimal dimensions of the prism. Now, how do I know that I'm solving an optimized question? Is when I see the word optimal or maximum or minimum, okay? So if I see any of these words, then I know that I'm solving optimal optimization question. So in this question, it's telling you that the volume is 5,000 centimeter cube and calculate the optimal dimension. So this is how I know it's an optimization question. So since I want to calculate the optimal dimension, what shape should it be? Cube, right? So I know it's a cubic shape. Now, what is given to me? What did they give me? The volume. So what formula should I start with? The volume, right? Because they gave me the volume, I have to start with the volume formula, right? The volume is given to me. So I have to use the volume formula. Does that make sense to you? So now I know that the volume of a cube is S cube. What's my volume? 5,000. I'm solving for what letter? S. How do I solve for S? Cube root. Because the opposite of cube is cube root. So to isolate for S, to cube root both sides, basically, right? So if cube root S cube, oops, what happened is these cancel. 17 point. And that's going to be centimeter. Right? That's easy. So the side length, right? The dimension of the optimal prism, right? So the dimension, because it's a word problem, the dimension of the prism is, or are, 17.1 centimeter by 17.1 centimeter by 17.1 centimeter. So that means that's telling me that the length, the width, and the height are 17.1. Does that make sense to you guys? Good. Now, some of these questions might not make sense because at the end of the day, my shoebox doesn't have to be a cube because it might not fit my shoe properly, right? Or the shoe properly. But then because they're asking for the optimal, it doesn't have to be the necessarily optimal for the object, right? And then, but you have to answer the question proper, like according to the rules. Again, it might not be the best solution, right? Because the shoe will probably not fit in there. Can we go to the second question? Yeah. All right, so the second question is telling you that the surface area of a pizza box, there's a mistake here. What's the mistake? Cube. What should it be? Squared. So this should be squared because the surface area has a unit of a squared unit, right? You guys are too smart for it. So the surface area of a pizza box is 45,000 centimeters squared. Find the dimension of the optimal pizza box. Now, at the end of the day, are you going to have a cubic pizza box? Is it going to fit properly your pizza? No, it's not. But let's solve the problem because that's what we're asked to. Okay. So the surface area. So I'm given the surface area. What formula do I start with? 6s squared. So the surface area is given to me. So I have to use the SA formula, which is SA equal 6s squared. Okay? I know what the surface area is. Okay? Now, how do you solve for S?
So like the S and put the 6 divided
Surface area divided by 6, you mean? Yeah, so first thing is I want to get rid of that 6 because I'm isolating for S. So bring it over, it becomes division. So 45,000 divided by 6. And then
square root.
Square root. Right?
Can we solve it one step or
You can.
two steps?
You can. Okay, so what would be your answer if you square root?
86.6.
Unit? So make sure you enter this properly in the calculator, right? If you are entering in the calculator, probably you either want to do the 45,000 divided by 6 first, then do the square root, or if you want to do it all together, make sure that you put this in bracket, okay? Because you want the whole thing to be square rooted. So therefore, the dimensions of the pizza box are 86.6 centimeter, yep, times 86.6 centimeter. What?
Why you have to put it 3 times again?
Again, dimension for 3D object, length times width times height. Right? So anytime you are reporting dimension of anything, like if you look at your, if you bought something and then they tell you the dimension of it, they give you 3 dimensions always, right? They give you length by width by height, right? This is how they report it, right? So when you're reporting your dimension, you're going to have to report all 3 of them. Are we okay with this? Good. So anytime it's a rectangular prism and we're trying to optimize, we're using the cube shape, which gives me the 6s squared for the surface area and the s cubed for the volume. Are we good with that? All right. Now, we're going to also look at optimizing cylinders. Okay? a lot of our bottles or cans, right? They all have a cylindrical shape. And as you know, companies, they want to save money and they want to make sure that their dimensions are proper for that particular object. Okay? So if I'm looking for an optimal dimension for a cylinder, the height should be equal to twice the radius. Okay? So if I'm looking at my optimal cylinder shape, okay, your height should be equal to your diameter, which is twice the radius. Okay? If they're equal, that means you have the minimum surface area and the maximum volume. Does that make sense to you? So the condition here is that your height should equal to twice your radius, which is your diameter. Okay? So what's my original surface area formula for a cylinder? So if I look here, the surface area for a cylinder is 2 pi r squared plus 2 pi r h. Okay? So 2 pi r squared plus 2 pi r h. We're deriving our formulas, okay, guys? This is what we're doing right now. And for the volume, it's it's pi r squared h. Okay. Now the condition for it to be optimized is h should equal to what? What's your height equal to? It should equal to 2r, right? So the height should equal to 2r. Can I have your attention? I'll give you time to copy this.
Oh, the diameter. Yeah.
It should equal to the diameter, but we're going to use the radius because I already have the radius in my formula. Okay? So the height is equal to twice the radius. So instead of using h, I can change h to 2r. Okay? So I can replace h with 2r. So I would have 2 pi r squared plus 2 pi r times 2r. Yes? Are we okay with this?
Yeah.
So I replaced h with 2r. Yes. But for it to be optimized, the height should equal twice the radius. So what I'm doing is I'm replacing the height with its value, which is twice the radius.
That's only when they have the same value.
When it's optimized. This is only when we're optimizing. Are we okay with that? So for us to be able to optimize, for it to be the optimal value, the height should equal to twice the radius. So what I'm doing here is I'm replacing h with 2r. My ultimate goal is to only have surface area and radius in my formula.
Yes.
Okay? So let's try to work this out. So simplify this. This looks too complicated. So that would be 2 pi r squared plus 4 pi. R times r is r squared. Right? What? It's not r and r squared for it to become. Okay, why is it 4? 2 times 2. 4 times pi. R times r is r squared. Yes. Are we okay with this? Common factor. If you have 2 pi r squared plus 4 pi r squared, what do you get?
No more factoring. What's the factoring?
If you have 2 pi r squared plus 4 pi r squared, what does that equal to?
6 pi squared.
Yeah. Why 8? You're adding, man. You have 2 apples plus 4 apples. That's 6 apples. Right? So the formula for the optimal cylinder for the surface area is actually 6 pi r squared. No, you're adding them.
Oh, yeah.
What? Okay, question for you. 2x plus 4x, what do you get?
6x.
It's not 6x squared, is it? No.
They're- the
Okay.
pies are adding, they're not finding.
You have 2 pi plus 4 pi. What do you get? 6 pi, right? If you have 2 pi r squared, as long as they're the same like terms, they have to be like terms. And in this case, they are like terms. The only thing I would do is I would add my coefficient. Right? They have to be like terms.
Yeah.
Then you can't add them. And that's why in example, for example here, they're not like terms, so I can't add them. I have to leave them like this. Right? But what happened is when I'm replacing h with 2r, they become like terms and I can add them. Yeah. So the surface area of an optimized cylinder is 6 pi r squared. So that means it's like the area of 6 circles, right? Does this remind you of anything? What was the surface area of a cube?
Reminds me, maybe that I was having.
Okay, question here, back here. What was the surface area of a cube? Of a cube? 6s
6
squared, right? So it's the area of 6 squares, right? For a cylinder, it's 6 times the area of a circle. What's the area of a circle? What's the area of a circle? Pi r squared. So you have 6. It's the same thing, but this is the area of a circle. This is the area of a square.
But how can it become 6 circles? That's what I'm not.
If you actually cut them, if you actually make this, that will be the area of that. It will be actually equal to 6 to 4. Okay? You don't need to worry about this. You just need to worry about surface area is equal to 6 pi r squared.
Can we put that formulas on?
Well, it's an open book assignment, man. Like you can do whatever. It will be right there for you. Okay. Now, how about the volume? What do I change? What do I replace h with? 2r. So pi r squared times 2r. How do I simplify this? 2 pi r cubed. Because it's multiplication. That's right. Yeah. Because we're multiplying them, right? R times r squared is r cubed. Are we okay with this? We're good? Okay. So, here's an optimization question. The surface area of a can of soup is 154.6 centimeters squared. Find the optimal dimensions of the can. So what formula do I start with?
6 pi r squared.
That's right, because I know the surface area, right? The surface area is given, I have to start with SA equals 6 pi r squared. I'm looking for the optimal dimension, right? So I will change SA to 154.6. Yeah, divide by 6 pi. And then square root. So be careful when you're entering this in the calculator. Okay? I'm just going to have to get a calculator 1 second. Try it and tell me what you guys are getting, and I'll tell you if I'm getting the same thing. 2.9. Did we all get 2.9? Make sure you enter it, because if you're not getting 2.9, that means you're doing something wrong with the calculation. Because we have a lot of multiplication and division, and then the calculator will not give you the right answer if you don't enter it properly.
So 2.9 squared or cubed?
Just 2.9. Did you get 2.9? Did we all get 2.9? Now be careful here. Can I have your attention here? So your radius is 2.9. What's your height? 2 times that. That's right. Because remember that your height is twice the radius. So if your radius is 2.9, then your height is 5.8, is it? 7? So the height is twice the radius. So that means your height is 2 times 2.9. Why is it 0.7? 5.8. Yeah. No, the radius of 2.9 centimeter and a height. This is not a cube anymore. So when you're reporting your answer, you're going to say the dimensions are a radius of 2.9 centimeter and a height of 5.8 centimeter. No. So for the exam, you would need these formulas, but on your assignment, it's an open book assignment, so you should be fine. Right? So, how about for the last example? So the volume of a Pringles container is 1800 centimeter cube. Find the optimal dimension of the container. What formula do I start with? That's right. Because I'm given the volume, right? So the volume is 1800. Divided by 2 pi. And then cube root to get rid of that cube. Yes. 6.6? Yes. So that's the radius is 6.6. Okay. And what would your height be?
Height is gonna be 12.
I think it's 13.
13.2.
So the dimension of the container the optimal dimension radius of 6.6 centimeter and a height of 13.2 centimeter. Can I, for example, add to this question and I ask you what would be the surface area or what would be the minimal surface area? So if I asked you that, what would you do to find it? So you can use 6 pi r squared, and then what do you do? Let me add a question here. So what is your minimal, that's an n, surface area? So what would you do?
What is your minimal?
So in this case, you're going to take the surface area formula, and then what are you going to plug in it? The radius, which is 6.6. So this is like, you might see questions like this, so you should know that at this point, you found your optimal dimension, you just have to plug them in. Okay?
Can you explain that again?
Yeah, just one second.
Sorry for being annoying.
So I'm asking you at this point is, what would be your minimal surface area, right? We started with the volume, right? I asked you to find your your optimal dimension. So you did find your optimal dimension. Now I'm adding to it and I'm asking you, what would be your minimal surface area here? What would be your surface area using this dimension, right? So in this case, you're going to take your surface area formula and then you're going to plug in the radius to find what your surface area is.
What confused me there is like you said your minimal.
Yes, because when you're looking at an optimal shape, you're always looking at your minimum surface area and your maximum volume.
That's the part that I didn't understand.
Yes.
Because if you're minimizing something, it's like you're making things smaller.
No, your optimal means this. Minimum surface area, because you don't want to have a lot of material that you're using, and then you're having the optimal volume. So you always minimize the surface area, so you make the surface area small because you don't want to use a lot of material, but you maximize the volume of it. Okay? It's like what we did yesterday for the chicken coop, right? You want to use the least amount of fencing, but you want to have the maximum area you have for your chicken. Right? It's the first sentence. Yes, if you go back to the previous page, right? We said the purpose of optimization is to minimize the surface area and to maximize the volume.